HumanBenchmark.com is a website which has these short little cognitive tests that you can do for fun. It also shows you how everyone else compares through a deviation graph. My goals today are to program something that performs better than a human and to have fun. I'll show you how. First things first, let's set a reference point. The first test prompts the user into clicking on the colored area as soon as it turns green. At the end, we will have a reaction time. This test shows an increasingly large set of tiles. Tiles flash and then vanish, and we're expected to click where we remember them to be. For the aim trainer, we are meant to click on the targets as soon as they appear. This is easier on a touchscreen, but I'll have a go with mouse. This baseline reveals some pretty good results, but we can do better.
From the moment I understood the weakness of my flesh, it disgusted me.
The default game in the website is a reaction time test. Let's break down how we can approach this. When the game starts, we don't do anything while the screen is red. When we detect green, however, then we click. For this project, I will be using the Rust programming language due to its fast execution speed and low level control. I begin by creating a new Rust project and importing the screenshots crate, which allows me to take captures of what is on my display. I test this out by taking a screenshot of my code editor. With the crate, I can also get some information about the screen, which will come in handy later. I also extract the RGB color values from the pixel in the center of my screen. Just know that each pixel is a combination of red, green and blue, each with values between 0 and 255. Now that I can read pixel values, I create a method for checking if a pixel is the same as the green from the website. I do this by storing the website's green as a combination of red, green and blue, which is shortened as RGB, which I can directly compare other colors to. My initial plan was to use the same data structure for RGB color values as the screenshots grade, but after failing to find documentation for it, I simply chose to create my own, which I used for the rest of the project. I created a constant of my RGB struct, which specifies the website's green, and then created a function to compare other colors against this. To verify that this works, I add a timer which stops the program at a specific point to allow me to switch to the website before my screen is captured and compared. Since this worked, I went ahead and added the Enigo crate, which allows me to simulate mouse and keyboard input to finally test out my code. At this point, my problem is that I need a way to start the script when I am inside the web browser on command, for which I implement a keybind using the rdev crate. This works by listening to system callbacks, essentially system events, and I can cause them to trigger a specific part of the program. However, this will make our program much slower, as I would have to listen for system events before taking a screenshot and then comparing the color of the specific pixel. I'll show you what I mean. The current thread, or program flow, is being oversaturated by too many instructions, and thus our frame rate and automated reaction time are horrible. To fix this, I turn to multi-threading, which is parallelizing the tasks. I can spawn a new thread, which is a separate program which runs at the same time, whose only responsibility is to watch for user input and update a flag to tell the original process to start monitoring for the color change. To further improve performance, I can use the scrap crate instead of screenshots. Scrap works by asking the operating system's compositor for the current screen contents, and we get a large array of pixel data in return, giving us a fast and real-time method of capturing our screen. Each frame that Scrap gives us is just a big array of bytes, representing all the pixels on screen in BGRA format. This means that every pixel is stored as the 4 consecutive bytes: blue, green, red and alpha. The data isn't given as a grid, however, but as a flat list. We index into this list using a single number representing the position of the data we need. If we wanted to get the second pixel of the second row from our display, we would need to skip one row length worth of pixels and then skip 2 items. This can be generalized by the method shown on screen. Keep in mind that there is a hard limit on our reaction time, which comes from system delay. The operating system usually has a few milliseconds of delay in updating our screen and sending mouse input. Let's see how we've done so far. With this, we can move on to. To support the aim trainer, all I needed to do was add functionality for a calibration mode, which would define a region of interest so we don't look for targets outside the real area, and updated the pixel matching logic. Now, we can just look at every pixel inside this region to see if it matches the inner color of the target. If it does, we simply place the cursor there and click. That's it. We can make this a bit faster by looking at every third pixel, but we are already close to the latency limit. To define a region where targets appear, we can create a toggle for the program to understand to read mouse input to define a box, similar to how you take a partial screen capture. We do this by creating another condition inside our separate input thread in a respective flag which the rest of the program can access. And soon enough, the aimbot works. And now, to wrap everything up, the steps for automating the memory game are simple. First, we detect when the tiles appear and snapshot them once, remembering their centers. And then, we wait until they are hidden to make the mouse click on every stored center. To check if the tiles are being shown, I ask, is there a big white blob inside the region of interest? If yes, then tiles are showing. When the tiles do show up, I just copy the region of interest into a buffer, so I don't recompute it every frame. Inside the snapshot, a flood fill groups connected white pixels into blobs. I then filter out dust in small shapes, such as the cursor, and then compute the centroids. Then it's just a matter of storing these and clicking the mouse at each one when the tiles are hidden. Since the tiles are also animated as they appear and disappear, I also define a time requirement for the white spots on the screen to be static, meaning that they are fully revealed. And that concludes building the project. Hey, you made it to the end of the video. I hope you enjoyed it. This was also my first time doing a long form video. If you enjoyed any part of it, consider subscribing so I have an excuse to make more videos like this. The project code will be available on my GitHub link below. Thanks for watching, I hope to see you again.